Okay, I continue with my talk on molecular engineering of ceramics, with ceramics, whatever the language is. Where I left off was with the statement that clays are layered structure, one layer after the other. It is just like this stack of papers. What I would like to do is take this stack and do engineering with it. So, these layers separate out more and I can put in newer materials into this between the layers. The uses are varied. One operation I had already said, as polymer engineers are already working, exfoliation of clays, put polymers in so that the polymer can be strengthened, and they have made significant process on that, polymer engineers and polymer technologists. Let us see in what are the other ways we can molecularly engineer these layered ceramics, and let us see how they can be used. First of all, let me start off with a diagram and then go back to explaining. So, let me finish the diagram first. Yeah, now that my diagram is over, here what I have done, I have taken the clay as it exists. I have increased the spacing between the clay layers, and then I have put in other oxide materials between these two layers and formed oxide pillars. Over here, what did I have to do? I had to do cation exchange. The smaller sodium, potassium ions which normally exist between clay layers have been replaced by larger cations. They can be metal complexes, they can be metal polyoxocations, even what I would can say is charged colloidal particles. And as they go in, they are then over here, they can be calcined, means heated, to form the oxide layers to give this pillared clay. The best known pillared clays are aluminium oxide pillared, which are formed by ion exchanging interlayer cations with Al 13 O4 OH24 H2O 12 7 plus. These are called Kegin type ions, and then they are heated to above 400 degrees centigrade when we get this aluminium oxide pillared clay. The interlayer spacing over here is about 8 angstrom to 10 angstrom, and the specific surface area can be as high as 300 meter square per gram, which is a very, very high surface area. They are very stable, and in this way, by pillaring of clay, we can increase the basal spacing of clays. Okay, we do that for what purpose? Let's look at what we can do. This is the original clay particle. We can increase the basal spacing by putting in salts. Here in this we can put in once we have put the salt in, increase the interlayer spacing, we can put in organic molecules which are very large, and after having done this, we can further ion exchange to give this sort of pillared clays. You see, why all of this? This is because these pillared clays can be used as carriers to have catalysts. You see, in today, suppose you are driving a car, the emission has to be controlled. It means that carbon monoxide has to be converted to carbon dioxide. The nitrous oxides have to be converted to nitric oxides before the gases come out into the atmosphere. So, obviously, catalysts are needed in the exhaust pipe to convert these. I had referred to this at the very start of my lecture as to what are modern ceramics trying to do to tackle greenhouse gases. In today's cars, what we have, if this is the exhaust, the surface of the exhaust has a porous body which contains these catalysts. And so, only the catalytic action will occur only near the surface, only near the surface. We will miss out the entire volume part. So, today these types of intercalated clays, where the separation between the layers can be made as large as 15 to 20 angstrom by means of pillaring, means large molecules of gases can pass through them. So, this pillaring has given rise to the industry's possibility of exploring them, so that instead of the gases flowing over a layer of catalyst, what they can now have is pillared clays over here filled with catalysts in the pillar region, and the gas flows through this, so that there is a large area of the catalyst available for oxidation of the emitted gases, emitted greenhouse gases. These clays can also act as selective adsorbents. Because each organic molecule has a definite size, we can control this layer separation very precisely down to an angstrom, because we are going to put in ions, as I did over here, to cause separation of the clay surface. Hence, if I got an organic molecule which is say 16 angstrom is its overall hard sphere, molten sphere, we have the clays pillared so that the intercalation distance is a 16 to 18 angstroms, nothing more. All we have to do is choose what we are putting in for pillaring carefully, have very good control on the length of the distance between the clay layers, that means the pillar heights, and that will adsorb only that diameter of the organic solvent or the organic material, and that particular material is obviously retained or filtered out from whatever processing you are doing. So, they can act as catalyst supports, selective adsorbents and the lot for industrial action. But one more thing can also happen when we are talking of selective distance of separation between the clay layers and having very good control over the separation at angstrom level, it allows us to have drugs put into these clays. We have got the clay, we have separated the layer out to the designed distance, which is the size of the drug molecule. Why? This I had also again referred to in very earlier alluded to in my earlier part of the lecture, is these drug clay nanohybrids can then be taken orally, and inside our stomach there would be slow ion exchange, so that the drug is released over a long length of time. These drug clay nanohybrids are a very essential, is a very excellent way of slow drug release in our body. For those of you who are not initiated, let me put in some stats. I can take a tablet, say I have a headache, orally. The same painkiller can be given to me intramuscularly. The same painkiller can be given to me intravenously. Now, obviously, the intravenous process is fast because the drug is released directly into the bloodstream. But for that, you need hospitalization. Here, 100% of the drug is almost used. When it is given intramuscularly, you still have to find someone who will have to inject into you, unless you are proficient with self-injection. Here, the drug usage, bioavailability is 70 to 80%. But once you take the tablet orally, the bioavailability can be as low as 10%, especially if you have taken it right after food. Because, and if you have taken it before food, 20%, 30%, nothing more. Because in our stomach, the drug goes in, there are a lot of acids that hydrolyze it, and it is the hydrolysis product is then absorbed in our gut. Whether it is given intravenously, intramuscularly or orally, where the question is of bioavailability, the other most important fact is how long does the action of the drug stay. You see, in most of the cases, the doctors will ask you to take the same drug over twice daily, thrice daily in many cases. Why? Because the drug has gone into your body, it has been used up, and after that there is no after effect. You are now as if you do not have that drug in your system. It is with this idea sustained release drugs first came into the market, where the drug would be released into the body over a long length of time. I mean orally taken drugs. With drug clay hybrids coming in, delivery of sustained release drugs has taken a quantum leap. Such drugs are now available due to this pillaring of clays, so that the entire drug is not released, but slow ion exchange occurs in the stomach, in the gut, and the drug is released over an 8-hour, 12-hour period of time, so that the number of times you have to take the drug is decreased. You see, one of the biggest problems of medical personnel or doctors is patient non-compliance. the patient forgets how many times he has to take it. He or she does not take it at proper intervals. And this drug clay nanohybrid offers a choice to have lesser number of doses, but with a sustained release of the drug. Now, this idea of drug clay nanohybrids have been further developed into what is called layered double hydroxides or LDH. This layered double hydroxides are basically made up again of oxide ceramics. Before the intermission, I had referred to this brucite layer, which is basically MgOH6 octahedra. The formula is magnesium hydroxide, but the octahedra is magnesium ion is at the center and it is surrounded by 6 OH. Now, they are oriented as per this. What can happen if I take these, the brucite layer, the magnesium hydroxide layer, and then have a cation between two layers? What I now can engineer is something like the pillared clays. In the pillared clays, we were separating out each individual clay platelet, pushing them apart. But now here we are working up to bottom up now. If I consider clay particle that is the top, I am breaking up it into layers, separating the layers, that is top down approach. But now with magnesium hydroxide based materials, I am working on a bottom up approach. Here I have got brucite, we just got layers of magnesium hydroxide over here and over here. They are all individual. You see, these octahedra are not yet connected because this is OH. All of these are H. So, this is one layer, this is a second layer which does not have any connectivity. But if I place an anion over here, a compensating anion, and any other divalent cation to compensate for the charge, what can I do? Depending on the size of this anion, I can have this distance under control. I can control the distance between these two layers. These are called layered double hydroxides. Before I go overboard, you see, this is another view of the same brucite layers. These are brucite layers. These are all brucite layers. The octahedra are pointing up here, the octahedra pointing down, and what we have is basically this, if we can control this spacing, we can control whatever we can put in. For example, a big idea that is carbon dioxide capture is a goal of today's technology, how to capture carbon dioxide so that it can be removed from atmosphere. Because in an automobile emission, okay, you are converting the CO to CO2, but you are still emitting the CO2 into the atmosphere. So, it has to be removed. One of the technologies that was in contention was this layered double hydroxide, where the carbon dioxide would be captured between the brucite layers. Now, why did I say it was under contention is another matter? Because nobody thought what would they do with all of this once the carbon dioxide is captured. There is a joke we all share. That is, yes, you write a paper, you write 10 papers, you write 100 papers saying, I have got this brucite layer, I have developed a way to capture the carbon dioxide. Fine, but then what do you do with it? Nobody has an answer. Nobody is going to send it out to out intergalactic space so that all the carbon dioxide can be released into space. So, people did not think of it, but what came about through that useless bit of 1,000 or there are really 100,000 papers on this subject is that at least we can use layered double hydroxides to capture other materials. But that work came out of this work, which was how to reduce carbon dioxide emission. You see, in this diagram what I show is again the brucite layers. I can, again in the bottom over here, brucite layers, I can change the distance between the two brucite layers by controlling the size of the interlayer anion. Here it is 9.7 angstrom, here I had a smaller interlayer anion, here the distance is only 7.6 angstrom. These are basically the ones that we are targeting for biomaterials application. I will come to that in a bit later, or rather maybe I should talk of it now. You see, our bone is basically HAP, hydroxyapatite, these are all hydroxyapatite layers with proteins occupying the space between them. What this layered double hydroxides have opened up is a chance for us to develop real synthetic bones which actually mimic the natural bone. As I was saying a few classes back, yes, ceramics like alumina have been used for orthopedic implants, but they are sintered alumina. They are as brittle as alumina is, and in many cases, especially where your long bones are concerned, which has to take a weight which will be subjected to alternate tensile and compressive load, it does not work. Rather, if we had such layered double hydroxides, where it would be a mixture of the ceramic with the protein, the chitosan, the organic polymer between the layers, we would get a material which would have higher flexural strength, higher impact toughness. So, today for example, with these layered double hydroxides, we are now seeing the possibility of having real synthetic bones. But more on that maybe later if I get time. Let us look at the possibilities of what we can do with these layered double hydroxides. I guess the diagrams as I draw would be self-explanatory, but yes, there would be voiceover. Carbon 60. What is it? A buckyball. Buckminster fullerene. Looks like a football. I would leave it to you because I had shown the diagram of Buckminster fullerene earlier in the lecture, that it has got 5-sided, 6-sided carbon rings, and it looks exactly like a football. I could put Buckminster fullerenes, carbon 60, over here, and this particular material is one which has got large scale introductions. First of all, to go from the layered double hydroxide to here, what was done was, in between the chains over here, over here, large organic molecules like say dodecyl sulfate was put into these two layers, thus having a large layer separation. And then they were in the carbon 60 was then pushed into these intercalated layers. This is one. We could also use materials like ferrocyanides, iridium chlorides, all of this in these layered double hydroxides, so that we have electrodes. We take ferrocyanides, iridium chloride and all of that, and here what we can then have is electrodes which are very stable and can work at very high temperatures. Over here, what we could also do with these layered double hydroxides is put in between the layers large functional organic molecules. So that the distance between the double layers of the double hydroxides can be changed, and this can be used as isomer separator. These layered double hydroxides can be, I only hope you are not confusing with layered silicates. Here I have started off with the brucite layer, I have added the anions or appropriate size, so that I have got brucite layer build up one over the other at controlled distances depending on the size of the organic molecules or the inorganic anions that I am bringing in. I am again reverting to this diagram to say that the size of this anion controls how far these brucite layers can be. The anion here is not exfoliating the clays, it is not forcing the clay particles, but rather they are taking the magnesia octahedra, the brucite layers, and stacking them at heights as per the size of this anion. If I require small distances, the anion shall be a much smaller one, whereas if you want to put in large distances, the anion shall be of the appropriate particular size. You see, why am I bringing all this in? LDH, use of layered double hydroxides, permits us to do things like this. That is, I can form bio-nanohybrids. I can take the layered double hydroxide, put in the DNA that I want, then implant it so that I can have, I will not use the term genetic repair as such because it has not been done, but that DNA, once it has been put into the cytoplasm, it is there for being integrated into the human system, because once it got to the cytoplasm, it is in the human system. So, here using this layered double hydroxides, it is not only drugs, but we can work at DNA level, where the DNAs bring in the layers of the brucite at appropriate distances, and then it is put into the body. You see, this bio LDH or bio layered double hydroxides are already in use in medicine. For example, an anti-cancer drug, methoxytetrate, if I remember correctly, that is now being injected into the system by using layered double hydroxides. Vitamin C is a good antioxidant. Many cosmetics today have vitamin C in them, not as vitamin C, but vitamin C intercalated between two in a layered double hydroxide. I won't go to say which layered double hydroxides, because that would be a violation of IPR, which is yet to be filed, but they are already in the market for drug delivery. Putting it in the cytoplasm, DNA repair, it is being worked on, but the results of such DNA delivery is not yet in the public domain. However, the point is these layered double hydroxides open up the possibility of its use in biological systems, especially in drug delivery side. The added advantage is targeted drug delivery, is that you have these layered double hydroxides, put the drug of your choice in, but at the same time cause ion exchange so that magnetic ions like iron can also be implemented. So what happens is, if I want the drug to be delivered to, say I have an abscess over here, I want the drug to be delivered over here. So what is being done is deliver the drug by intravenous method, focus a magnetic field at the point, a high energy magnetic field at the point where you want to have the drug delivered. Because the LDH has the drug and also the magnetic material, it is automatically directed to where the magnet is being focused, and there it goes in, resides, and the drug is delivered to the body through ion exchange reaction. The use of layered double hydroxides has been in the more in pharmaceutical industry, wellness industry, means lot of face creams are there which use layered double hydroxide so that you can get under your skin, swell up and remove the wrinkles. That sort of layered double hydroxides are already available in the market, and I had alluded to this at the start of my lecture. As I said, hydroxyapatite, the synthetic bone, is a very desirous material for layered double hydroxide. In addition to layered double hydroxides, we have layered metal oxides also, where the basic idea is again using these oxide double layers, layered metal oxide layers, to work like layered double hydroxides. Perovskites, I won't say what it is. For example, calcium titanate is a perovskite. Perovskites are a very important classification of layered double oxides, simply because of the inherent structure of the perovskite. Basically, they have got octahedra, which are either, which in all cases they are layer like the layered double hydroxides, and you can intercalate these layered metal oxides with a lot of other compounds. Because you see that if I draw it, hopefully I will draw it clear, because I always tend to mess this drawing up. This is where I mess it up. So, this is one layer of perovskite, this is second layer of perovskite. Now, I am going to target a few places and see what happens. I place a cation A over here at this particular place. Here I will have less covalent and weak bonding. In this part, I got less covalent bonding. So, basically, in such structures of layered perovskites, I can cause exfoliation and put in different ions so that they are trapped in places like this, and I have got now a layered metal oxide ceramic composite. But other than layered metal hydroxide ceramic composite, what has become possible is solar cell material. Like say cadmium sulfide, all of these materials can be synthesized, put in using these layered hydroxides, giving the hybrids of the perovskite and these particular phases. So, in a sense, over the last 3 lectures, what I have tried to talk of is, other than bulk forming and thin film deposition, we have technologies in ceramics where we can deposit these materials layer by layer. That is when I was talking of self-assembled monolayers, and here today I talked of organic, inorganic, nanohybrids, if you wish to say that. And both of these techniques require much less processing temperatures, are much more environment friendly because they are grown from the solution state up to give us the final product. What you have to remember is the work on this SAM, you saw when the first Langmuir Blodgett film was made over 60 years ago. It is still a technology which has to be developed. And this technology is now developing at a very rapid pace simply because of greenhouse gas emission problems. It is not possible for me to cover the entire or it was not possible for me to cover a larger section of these self-assembled monolayers, layered double hydroxides, but being an advanced course, I am sure that you would be using these technologies in the coming 5 or 10 years. It is that close, but once it comes in, it is something that will take the world by storm because it's much more environmentally friendly.